Welcome to Exploring AI Matters. This podcast series, previously known as Mind the Gap, Dialogues on Artificial Intelligence, will continue to appear in the ABA series to the extent that. In addition, all of the episodes, old and new, will now appear under our new podcast name, Exploring AI Matters. Thank you.
For thousands of years, we Earthlings have been fascinated with the night sky and its myriad stars. Beginning with Galileo's first telescope and accelerating ever since, astronomical instruments have dramatically expanded our ability to examine the things we see in the night sky. For example, an old issue of Scientific American, published near the end of the First World War, contains an article entitled "The Heavens in August 1918. It reports on a great new nova in the constellation Aquila. A nova is a star that suddenly and for a relatively short time becomes much brighter than in the past. This report notes that the only other nova of modern times had been discovered 17 years earlier in 1901. In a YouTube video dated July 22, 2021, our guest for this episode, Dr. Becky Smethurst, explains that the classic type of supernova is a massive star 10 times the size of our sun that runs out of fuel at the end of its life. Essentially, gravity starts to crush it inwards. Finally, all of the outer layers of the star rebound off the inner core and get thrown out in a huge explosion. Today, the rate of discovery of novas has increased dramatically. One of the reasons? Our instruments survey so much more of the sky, both in angular area and depth, which means we capture more such events. Greater depth means farther away in space and thus further back in time. For example, the Vera C. Rubin Observatory Telescope is scheduled to be launched in October 2022 and to become operational about a year later. It is estimated that the Rubin telescope will photograph the entire available sky every few nights. Experts predict that it will discover 3 to 4 million supernovas over its projected 10-year service life. This deluge of data has exceeded the capacity of traditional astronomical analytic processes, in which trained experts, usually graduate students, pore over and analyze the raw data. Astronomers and astrophysicists have lately been exploring two new pathways: crowdsourcing using systems like Galaxies and artificial intelligence. The flood of recorded observational data enables us to ask questions about the stellar universe or cosmos that 100 years ago would have been incomprehensible to anyone hearing them. Like, which comes first, the formation of a galaxy or of a black hole within it? In this episode of Mind the Gap, Dialogues on AI, we talk with Dr. Becky Smethurst, a research fellow at Christ Church College, Oxford University, whose research concerns questions like, do galaxies and black holes evolve together? And what influence does a supermassive black hole have on matter near its event horizon and on the galaxy it is at the center of? We are particularly interested to ask her how astronomers are contemplating the use of AI to sort through and analyze the data. Dr. Smethurst is at the leading edge of the use of artificial intelligence in astronomical research. We encourage you to take an evening and read her short book, Space, 10 Things You Should Know, or watch some of her YouTube videos published weekly that explore questions about stars, galaxies, and black holes. Hello, I'm Roland Trope, a national security lawyer.
And I'm Charles Palmer, a computer scientist. We are your hosts this week for this episode of Mind the Gap, Dialogues on Artificial Intelligence.
In addition, we have two more hosts.
Mark Donner, a computer scientist, and Alma Adams, a national security lawyer who can't be present today.
Each episode will be led by two of us, with the other chiming in with impromptu questions as they are moved. So, Dr. Smethurst, I've been looking forward to this for weeks, ever since I discovered your YouTube channel. Please tell us a little bit about your area of research and
Mhm.
why is it of interest?
So my area of research is all about supermassive black holes. So these are the black holes that are millions to billions of times the mass of the sun. And we think that they live in the center of every single galaxy in the universe. And my question is, how do black holes grow? And most people sort of look at me like I'm stupid when I say that, because they're like, well, aren't they just sort of the hoovers of the universe, sort of like the vacuum cleaners of the universe? But actually, it's really difficult to grow a black hole. And the way that we've thought that happened in the past is that two galaxies merge together and their black holes merge together in the middle, and the two grow together. But my research looks at galaxies that have never merged with another galaxy. And we find that their supermassive black holes are just as big as all of the rest of them. So it's sort of thrown the cat amongst the pigeons a little bit on how black holes grow. That's my research. How I got into it, I like to tell people that I was a why child. I'm one of those kids that constantly is like, why this? Why that? Why this? And I think I never lost that as I grew up. And I think all scientists will probably say the same, that you have to have that natural curiosity to keep asking questions. And for me, the thing that fascinated me the most was space. Mm-hmm. It was just the endlessness of it, and the fact that you could see it with your own two eyes at the same time, these things that were so far away. And for me, it was always the mystery of it that intrigued me the most. So the fact that I've ended up studying black holes it's probably because the mystery of it always intrigued me the most. Mm-hmm. Black holes will always be these mysteries to us because they are these areas of space where there is so much matter that the force of gravity is so strong that light cannot even escape from them. So there's no way we can get any information about what's inside a black hole, if you will. And so we have to be clever about how we study them. We have to study the stuff around them to figure out what's going on.
What a puzzle. But like you, as a child, I had always been interested in astronomy and considered majoring in it. And I don't think I was quite good enough. My telescope was great, though. But I always imagined if I did this as a living, I would be an astronomer up on a hill, freezing to death, while looking through a periscope late at night. In fact, my mother even said, "You'll never meet girls. You'll always be on the mountain." Is that how things go now? Are you up on a mountain?
You can become like a professional astronomer that runs an observatory. So like, for example, there are people at La Palma in the Canary Islands, or in Hawaii, or the Atacama Desert in Chile that spend months at a time there operating the telescopes. But my role is more that I pitch to use those telescopes for, say, 3 nights, 5 nights in a year. And I might do that once or twice a year, get the data I need, and then squirrel back away to my office to then do the science on it that I want. So there are nights that you spend sort of with the people who are experts in using these, billion-dollar facilities that we build in order to observe the sky. And they are some of the best nights as well. You literally switch to working nights and you get to set the telescope off, sort of taking an image that's like 20 minutes exposure or something. And you think, oh, I'll just pop outside while it does that, and I'll go look at the night sky, and that's incredible. But the majority of my time, it's an office job, right? I'm sat at my desk, I'm at my computer, I'm crunching through data, but it's data that I want to crunch through, right? I want to be at the desk and I want to be there because the answers you get out at the end is what you're in it for, right?
So is that one of the main differences between an astronomer and an astrophysicist?
Mm-hmm. Yeah, exactly. An astronomer is someone that observes the sky and says, oh, look, there's a supernova that's gone off there. That wasn't there the day before. An astrophysicist is someone to go, okay, we've observed this supernova. It has these properties. What is the physics behind what's going on? I am an observational astrophysicist. So I actually use telescopes. I am an astronomer and an astrophysicist, but I have colleagues that probably couldn't even point out to you where Orion is, because all they do all day is they simulate the universe on computers, or they're very theoretical and they're working with equations on a blackboard or a whiteboard, I guess, these days. And so, there are astrophysicists solo and there are astronomers solo, and then there's some of us that sort of sit in the middle between both of those.
Great.
And you mentioned that you pitched to get a few nights a year. How can that small sample give you so much to be able to then squirrel away, as you say, in your office studying it?
Yeah, so that would be in telescopes that are designed for that. They're designed for what we call follow-up from huge surveys. So, for example, one of the largest astronomy collaborations is the Sloan Digital Sky Survey, which is a US-based telescope in New Mexico. And it's been running for 20 years, essentially just observing the night sky night after night after night after night, taking images, little postage stamps that it adds up, gets more and more light from each part of the sky each night. Then we can catalog that and say, okay, if you're interested in something specific, you can find them in that catalog. But that might not be the observation you need. You don't just need an image. You might need what's called a spectra, where you take the light, split it through a prism, and look at all of the individual colors and wavelengths, the fingerprint of light from that galaxy or that star to tell you more. And so then that's when you might pitch to another telescope, say, I have picked out these 10 things or these 50 things in this survey that I then want to follow up more detailed. And that's what you'd pitch for a telescope for. And sometimes, the newer telescopes or the newer instruments are very oversubscribed. Like the number of nights they have to give and the number of nights that people apply for is sometimes, 10 times oversubscribed for some of the more popular telescopes. So it's competitive as well.
What would you say is the most remarkable discovery by astrophysicists in your lifetime?
In my lifetime, to be fair, there's a couple I could pick. I think for me, the discovery of exoplanets, the fact that there were planets around other stars in the Milky Way that are not the sun, was monumental. I think everyone had always sort of assumed they had to be there, but actually finding it in the mid-90s. And then by the late 2000s, when the Kepler Space Telescope was launched, finding thousands of them after that was monumental. I don't remember it, though, because I was a young child when the first one was found in something like 1995. I think I was probably watching Toy Story or something instead. The one I remember that I think is the almost bigger than that in a way is the discovery of, or the detection of, gravitational waves. So this idea that space is actually a thing, that, mass can curve it. And if you have two big black holes that merge together, they're going to send ripples through space. And we can detect those ripples as sort of space compressing and stretching. A, the fact that we can detect that is amazing. And B, it was the first time we'd ever observed something in the universe, got information about something in the universe that wasn't in the form of light. It was a whole new way of observing the universe that we had never had access to before. And I think almost that's more monumental in the fact that, because it's the idea of other planets exist, or we're not that special. It's almost like just a reminder to us. But this was a whole new way of observing the universe that we never had before. And I think that will revolutionize the field more than anything else.
And it changes your research also?
It will, yeah. It has some implications. Not so much my area of black holes, because I work with supermassive black holes. The waves that they detected were from what we call stellar mass black holes. So, maybe like 10 to 30 times the mass of the sun, rather than millions or billions of times the mass of the sun. But it has implications for how small of a black hole can you actually have form from like a supernova or something like that? Instead of getting what's called a neutron star, it tells you what that limit is, which is really interesting in sort of all the ideas of how do black holes form in the first place.
Now, you said something just a few moments ago about black holes merging or colliding. And I have to say, when I was a young child and I loved looking at the sky and tried my hand at amateur astronomy, I never would have imagined that anything I was looking at either had in the past or would in the future collide. Could you explain something about that galaxies possibly collide, and maybe even our galaxy with Andromeda Galaxy might someday collide?
Yeah. So our nearest big galaxy neighbor is Andromeda. If you live in the Northern Hemisphere, you will be able to see it. It's sort of a fuzzy patch in the sky, which is amazing that you can see that. But it's actually about the size of sort of like 6 full moons across in reality, if you could see the whole thing. And it is coming towards us in the next 2 to 5 billion years or something. It will collide with the Milky Way. Now, I use the word collide very loosely there because space is very big. Wasn't it what Douglas Adams, like, space is big. You won't believe just how mind-bogglingly big it is, right? The space between stars compared to the space that the stars in the galaxy take up is tiny. It's almost like, how you learn how the majority of an atom is empty space, like 99% of an atom is empty space, right? The same thing is almost true for a galaxy. The majority of it is empty space. So when the two collide, the better word is probably merge, because no two stars will collide when the galaxies collide. Like, I think I worked out the number, like the probability once for a YouTube video, and it was astronomically small. It was tiny. And so when the two do come together, it'll be more like a redistribution of everything that's in the galaxy, just sort of getting sloshed around a little bit. But black holes can collide, can actually fully merge and become one black hole. And that's usually because our sun is actually quite rare in the fact that it's by itself. So 85% of stars are not by themselves. So it's quite rare in that fact. Most of them are in what we call a binary or a tertiary system of 2 stars or 3 stars all orbiting each other. So you can imagine if you've got 2 massive stars that form together and are orbiting each other, and they both go supernova and become black holes one day, those black holes are also still orbiting each other. And so that eventually those two things, having such strong gravitational fields, they will merge together. They'll spiral in and merge together one day over millions and millions of years, because these processes take a lot of time. But that is what we think happens. And that sort of mitigates the problem of space being very big and the idea of collisions being very rare, because you've already started with a system that makes it so that merger will be very likely. And it's why we've discovered over 30 or so now of these instances of either a black hole merging with another black hole, or a neutron star merging with another black hole, a neutron star being like the pre stages of a black hole. If you add enough mass to a neutron star, it will collapse and become a black hole.
Could you give us an idea of how much information astrophysicists will be gathering once the Rubin and Webb observatories are in space, operational, and collecting data, assuming all goes well?
Yeah. So the Rubin Observatory is actually a ground-based telescope. It's actually going to be in Chile, which is quite exciting. And so it still will collect a lot of data. So the survey that I mentioned before, the Sloan Digital Sky Survey, is the one we have now. That surveyed the northern hemisphere sky to, a certain depth, not very deep, just getting sort of the nearby stuff. And that gave us 1 million galaxies, which was already far too many galaxies for a person to look through. And when the survey was completed, sort of mid 2000s-ish, that was far too many for the AI at the time to also classify. And they did not do a good job on it, basically. The Vera Rubin Observatory, which is hosting the large synoptic sky survey, is thought to be going to be able to detect about 1 billion galaxies. So, I mean, that's not just an order of magnitude, that's a couple of orders of magnitude larger, right? Even if you can classify all those galaxies, the shape of them, and you manage to get 99% of them classified to a high enough standard that you're happy with it, that's still 1 million galaxies that you've got left over, if you've got a sample of 1 billion. Just because the telescope is observing further out, you're going to collect more and more lights. You'll see fainter things at larger distance in greater detail as well than we've ever been able to see before. So it's a lot of data. It's a huge amount of data. It's the point where people are worried about, where on earth are we going to store this data? And how are we going to let people access it at any time from anywhere in the world that's scalable? And it's a very interesting problem. One that raises, not just data storage, but also, what are you going to do with 1 billion galaxies? Are they actually all going to be eyeballed at some point by someone? Because a lot of the stuff that's in the Sloan Digital Sky Survey has still remained uneyeballed because it's been sat on computer archives, because 1 million is a lot. So there's the question of, this idea of big data, reducing stuff to numbers, and you can work with statistics and population, but you can't help but wonder how many of those will actually be seen by human eyes.
So with all of that enormous amount of data, which is harder, I think, for most of us to even quantify or imagine in our heads, when did astrophysicists start to use AI to grapple with all of this data? And how have they done so?
Yeah, so very early on, I think astronomers were sort of an adapter of AI for what it could do. I think because, we've been simulating the universe for so long, it was one of those sort of steps of like, okay, we are the imaging science. So using AI to classify images is kind of the thing that we should pioneer in a way. the problem that you have is that imaging specifically is very difficult for machine learning and artificial intelligence algorithms to do. I could show you a picture of a zebra right now, and a 4-year-old would know that it was a zebra and not a lion. But a machine learning algorithm doing that with images is very difficult. It's why when you have those "I'm not a robot" checks on the internet, that the recaptures, they're always images, because we're still trying to train machines to recognize certain things in images. And so to train a machine, you need huge, what we call gold standard data, sort of expert data that's classified, that it can be trained on to say, this is a spiral galaxy, this is what you should be looking for. This is an elliptical galaxy, it's a big blob, this is what you should be looking for. The thing is, there's so many in-betweens with images that you can have that don't fit into those nice, neat little categories, which is where a machine struggles. So there was a citizen science project called Galaxy Zoo that was set up back in 2007 to actually classify the shapes of those 1 million images of galaxies with the public's help. And, that thought it would be about 10 years before that would be done, before getting through all 1 million images. And it took something like 6 months. And that was fantastic, because that solved that problem of, well, we can't have the machine do it. Okay, the public has managed to do it, and 20 odd people have looked at each image and classified all 1 million galaxies, and great. That also then means that you have this training set. And so there was what's called a Kaggle competition. Those who are very big coders will understand and know what a Kaggle competition is. But it's essentially a competition between coders to say, who can write the best code to do this? And there was essentially one of these to say, who can write the best machine learning algorithm to classify these galaxies to within agreement with the public who've previously classified them, of say, let's say over 90%, 95, 97, how high can you push it? And everyone who entered that competition was finding that the training set just wasn't big enough. They were saying 1 million galaxies is not enough to teach the machine to what to look for. And the person that won it actually realized that the classification of an image didn't change if the image was mirrored and reflected. And you could do that sort of 4 times in sort of like a rotation of the image and still have the same classification. And so he managed to boost his training set to 4 million. And that was just about enough to get you somewhere in the range of like 95, 96% agreement with the public's classifications of it. And so I think that probably helps understand where the struggle is coming from. It's just that there's so many different nuances in images, especially with astronomy images, where you could have a satellite fly across the image, or you could have a cosmic ray, which is a very high energy particle from space, hit your detector, and you could have this big blowout on your detector or something like that. You could have 2 galaxies merging, which then affects your image as well, because then the computer's like, which one do I classify? And then obviously the biggest thing with machine learning is, what about the things you don't tell it to look for? Are those things going to remain undiscovered in the data because you only told it to look for certain things? And the things that look weird, the computer won't know that they look weird, and so won't flag it like a human would. So I mean, that's kind of the difficulties that we have in astronomy.
So how confident are we in the quality of the classifications that were done by the humans in this crowdsourced thing? I mean, you didn't eyeball all 1 million of them.
No, exactly. So that was a huge thing as well. So you can almost, there's like 2 stages to this. You have gold standard expert data. So someone like myself would classify a few of them, and you would see for each person, you would show them that image. Do they agree with the expert classifier? So then each user essentially has like a trustworthy score, if you will. It's not a score of how well they're doing. It's just that you can really easily filter out trolls this way. So you have a couple of different types of trolls. A troll that comes along and randomly answers. And you can pick those out because they'll never agree with the experts, and they'll also never agree with the crowd hardly either. So you know to downweight their classification basically, and not sort of think it's that important. There's also trolls that will come along and say the exact opposite of what it is every time. And hilariously, they're really useful because all you have to do is flip their response and you get the right answer, and you can add the crowd. This is also why you get more than 20 people to look at each image as well, though, because then you have statistics on each image. So sometimes an image is too hard to classify. It will be something very fuzzy, something very far away. You can't really discern any detail. And you can usually pick that out in the classifications because the vote essentially has been split across the crowd. We call it crowdsourcing these classifications of these images through citizen science. And this is really what it is. So there's lots of different ways that we can A, filter out classifications, or B, know when something just isn't classifiable because of the nature of the image itself. And those unclassifiable ones tend to be the ones that computers struggle with as well. So, there's lots of things that you can do to make sure that, you can trust the classifications you have.
When you speak of classifications, though, is this a fixed set of categories, or is that set constantly growing as you look at more and more varieties of constellations?
So we're not looking at, so constellations is just
No, I didn't mean constellations. I meant galaxies.
Okay, sorry. Yeah. So with Galaxy Zoo, what we did was we provided people set answers. So we'd ask specific questions. Is this a spiral galaxy or is it smooth and roundish? And people would have to decide. And then you'd go through sort of like a decision tree, like a Cosmo quiz, almost like this or this, right? People would make their way through that. With machine learning that we use, obviously then a machine is trained to then classify with the exact same classification system. That would obviously be trained machine learning. There's something else you can do, though, which is unsupervised, it's called, rather than what I just described, which was supervised learning, where you tell it to look for certain things. Unsupervised learning, you essentially would just feed everything you've got to an algorithm, and the algorithm would decide how to group things. And so it would hopefully group things as here's all the spiral galaxies, here's all the blobbish galaxies on sort of like two different clusters. So there's different ways you can go about this. But with what I do, we're really interested in specific shapes because we know that that's how we'd classify them. It's how Edwin Hubble classified them back in the 1920s. And it's sort of stuck in the same way that the biologists have their, classification animal tree, everything like that. We have a similar thing for galaxies. And so we want to know those classifications because we're looking for specific things. There are other people though, who are like, I want to find the weird stuff that doesn't fit into any cluster that a computer can find, and it will spit out, here's all the weird things. And so that's where you would maybe then use something like unsupervised learning.
And is there some sort of set number of these classifications, just a ballpark figure?
Yeah. So the first iteration of Galaxy Zoo was 1 million images classified at least 20 times by each, classified by 20 times in like 20 different people. But then there's a certain amount of clicks, obviously, within the decision tree that you have to make your way down, the maximum of which I think is about 12. So it's at least 20 million classifications, but number of clicks is going to be 2,400 million. So I guess that's 2.4 billion in US speak. So yeah, it's a crazy number of clicks that was sort of crowdsourced. But in terms of like classification, if a computer or an algorithm was doing this, then yeah, it would be, if you had 1 million galaxies, you'd get 1 million classifications out the back. But I mean, the decisions to make that, if you're thinking about algorithm jumping around stuff, perhaps following a chain, then you're talking way more than that.
Could you compare for us? Sorry, Mark, did you have something you wanted to ask?
Go ahead. That was me. Go ahead.
Oh, sorry. Charles, go ahead. You.
You're sounding more and more like an AI researcher because these are the kind of topics I discuss with my students.
Sure.
So how exactly, is this how you're using AI in your work? Or is it a little different?
No.
Or?
At the minute, stuff has changed, actually. So this was very early work with Galaxy Zoo and everything we were doing. Now things have changed a little bit in the fact that we are utilizing the machines and humans together. So now we have an AI on the back end of the Galaxy Zoo website where we ask people to classify these images. Because, even though those first 1 million were done, us astronomers are not going to stop taking pictures of the sky. So there's constantly more that needs to be classified. And what we have is a machine working in the background. And this is, for those who speak machine, it's a convolutional neural net. And it's active learning. So the machine is actively learning as more classifications come in all the time. It already has learned from a different classification set that might be from a different telescope or something like that. And it's already probably gotten rid of the ones that it is very confident that it can classify. So the things that are very obviously just big blob of a galaxy, nothing special, just quite round, very smooth, very flat. And the things that are very obviously giant, big, beautiful spiral galaxies, it will be very confident of its classification. And this is the thing that's so special about this algorithm, is that it does give you a confidence level on its classification as well, because of this active learning. And so those, it will probably never show to a human, because it's like, I don't really need the help with this. I've got it. The machine will make a decision, though, about what galaxies to show the humans and to put on the site. And the fun thing is that, as we launch this, people worry, well, I'm not going to see all of them. What if I miss something cool? The cool ones are usually the ones that the machine can't classify. It doesn't need help with the boring, fuzzy blobs. It needs help with the stuff that looks weird and wonderful, that it's like, I have no idea what this is. I need a human to look at this. And so this is how, moving forward, we think we're going to tackle something like the Vera Rubin Observatory, that we think is going to give us 1 billion galaxies after the survey is complete. Okay, maybe the machine can do 99% of them, of the easy ones, leaving still 1 million very more difficult, weird, and wonderful things for the humans to look at. And so this is what we're doing right now with Galaxy Zoo. And it's really helpful to me, because the stuff I study is the galaxies that haven't had mergers. And you spot those because they're not these big blob of galaxies that have been formed when stuff all gets rearranged in a merger. They're the beautiful, pristine spiral galaxies that have been left alone their entire life. And so picking those out, they're very rare, is obviously something you need either humans or a machine to do. And at the minute, out of those 1 million that we had originally, we have 100 of these things. Just goes to show how rare they are. So the fact that we are getting a sample that's not Northern Hemisphere, like the original survey we had was, but Southern Hemisphere with the Vera Rubin Observatory, different galaxies, 1 billion of them, not 1 million of them, it's going to increase our sample size a huge amount. But picking them out without, this machine that we've trained on all the previous surveys to do this was going to be so difficult. And so we can see this future where it's sort of like, humans and machines working together. Sort of, you got this friendly robot behind the scenes being like, I got this, don't worry.
Well, that's sort of like the folks who say AI stands for augmented intelligence, where it's a combination of human and machine. I have to ask, how many people were involved in the zoo thing?
Yeah, the Galaxy Zoo. So Galaxy Zoo actually was the first of these citizen science projects. It actually spawned a huge number of them called the Zooniverse, which has everything from astrophysics projects to zoology projects about the Serengeti and penguins, to now historical projects where they've scanned in like World War I diaries and are asking people to, what's the word?
Transcribe.
Thank you. So everything to like historical documents that have been scanned in, World War I diaries, where they're asking people to transcribe, to digitize what they see, right? In terms of dates and locations and everything like that. So the Zooniverse is, I probably couldn't give you a number of researchers that are involved. There's probably thousands around the globe. In terms of the number of volunteers, the Zooniverse is over 1 million. I think it might be 1.5 million now. It's a huge number of people worldwide. Galaxy Zoo, I know, is about 300,000 people that volunteered worldwide to do the classifications. In terms of number of researchers, we're probably around about 30 that have various different projects, and they're based in the UK, the US, Australia as well. Real sort of like international project. Also in Europe too, in the Netherlands. In the US, we're based at the Adler Planetarium in Chicago, is sort of like the headquarters, if you will, for those who've been. But it's also people in Arizona and Minnesota as well. So it's a really, really great collaboration, actually. And it's a really friendly collaboration as well. And a lot of astrophysicists, but also we've brought in, some computer scientists as well, with this notion of, we want to make sure we do this AI machine learning stuff right.
Yeah, you're reading my mind again. I was about to ask, how closely are you collaborating with computer scientists to push forward?
Yeah, very. So we just had a PhD student finish up at Oxford whose project was essentially machine learning with the Zooniverse. And he essentially wrote a lot of this back-end code for the friendly robot at the back of the website that decides which galaxies to show people. That he was jointly supervised by a professor in the astrophysics department, but also a professor in the computer science department as well at Oxford. So that was a really nice joint collaboration where he really got to do both of getting to grips with all the astrophysics side of things and the astronomy side of things, of like what's important in terms of these images, the image processing, all the artifacts in the image, what's real, what's not, that kind of stuff. But then also the computer science side of things as well. And he'd applied his knowledge that he gained in this PhD, not just to this, but also to, if you heard of fast radio bursts, it's sort of the biggest mystery at the minute in astrophysics, is trying to explain these. And there's a telescope in Canada called CHIME that's essentially been, switched on for a couple of years now, just listening out for these fast radio bursts at all time. Picking them out, though, of just that noise of radio data is very difficult. And again, machine learning can be used there to pick those out. So there's lots of different applications in astronomy. And we were, very lucky that we could, fund a PhD student to do something like that, but also get someone to do it for this problem of we're going to have too much data in a couple of years.
Well, one of the cool things that seems to happen when you start applying AI in new areas is that you discover, and you may have mentioned this earlier, you discover weaknesses in the AI or techniques that might work for identifying zebras, but not so much for black holes. So are there weaknesses that machine learning is? I mean, it's not just benefiting astrophysics, it's benefiting machine learning too?
Yeah, one of the big things that we noticed was that some of the techniques that can be applied in other areas can't be in astrophysics because, for example, image machine learning can learn a lot on color. And the thing is, color is very important in astrophysics because it tells you a lot about the astrophysics of what's going on in the galaxy. If you have a very blue galaxy, that means it's full of a lot of blue stars. Blue stars are the hottest stars, the youngest stars, and the biggest stars. So it tends to mean you formed some stars recently if you've got some young stars in there. Red colors, or what we call red, it's an astronomer's red, it's very yellowish, really, is more of a sort of a dying embers of the fire. It's the smaller, cooler, older stars that live longer. The stars are very much like live fast, die young. If you're bigger, you have to burn through your fuel quicker to resist the stronger force of gravity crushing in. So even though you've got more fuel, you have to use it quicker, and your lifetime is something like 100,000 years as opposed to a much smaller star like the sun, which will live 10 billion years. So when you see yellow, you think, okay, well, that's not formed a lot of stars recently because all the blue ones, the young ones, have died off. And the thing is, if you see something that's maybe a little bit far away, so it's a little bit fuzzy and it's yellowish in color, people would probably assume that it is also not a spiral galaxy, because the other thing that we see is that when two spiral galaxies merge and they become this big blob of a galaxy, this what we call elliptical galaxies, well, everything's been redistributed. A lot of the gas that makes stars, the hydrogen gas, gets used up in sort of a big bender of star formation, essentially. And you get left with what we call a red and dead galaxy that is also elliptical in shape. So color can bias your shape classification. If you see a reddish color, you might think, oh, well, then that must be one of these elliptical galaxies and not a spiral galaxy. And for a long time, people were biased by that color. And it was only with the first iteration of Galaxy Zoo that we were like, actually 30% of red things are spiral galaxies. And that was because we didn't tell the users, the volunteers, anything about color. So they did not have that bias going in. And so therefore people could pick this out. Again, it was part of the sort of big population of things as well. You had that benefit of being able to pick out those big numbers. But still, that was a lot of galaxies, more than people thought. Machines also learn based on color. It's part of an image. It's part of the information that is in an image. And so again, especially if you're feeding it classifications that are perhaps also biased by color, then the machine learns the same bias. So that is one thing that we've struggled with astronomy, is that if you have that kind of color information, that can bias things. Also, as well, you can be hugely skewed if something, if you're only focused on, say, the galaxy in the middle of an image, that's what you care about, but it's in a very dense field of galaxies, like it's perhaps in a very dense area of the universe, where you have like a cluster of galaxies together. How do you tell a machine to just focus on the thing in the middle, and we'll get constantly distracted. The other thing about those dense fields as well is that they act as these big lenses. You know how if you take a wine glass and you have that stem with the ring at the bottom, and you can put it in front of a candle, and you can see the flame from a candle make this beautiful ring because of the wine glass stem acting as a lens. Galaxies can act as the same thing, but instead of glass, it's gravity that's doing the bending of the light, and so they bend the light from more distant galaxies. More distant galaxies are from the earlier universe, where it was denser, there was more gas to make more stars, so the galaxies are bluer. And so you end up with these blue arcs in your image. And a machine learning algorithm, if you just feed it that thing, it's like, oh, something blue, it must be a spiral galaxy. And you're like, no, these are these arcs, these background galaxies. These are these lensed objects that aren't galaxies in the cluster that you're bothered about. And so there's so many of these different biases that you have to try and mitigate in your algorithm somehow take into account and get rid of these biases. And that's quite difficult in AI.
Yes. And in fact, I saw an article, the beads, the little diamonds that Einstein predicted were just seen for the first time. Fascinating. So, okay, so you've found some weaknesses in machine learning techniques, and they're learning from you as well. If you could pick an improvement or two, what sort of improvement would you like to see?
I mean, it's funny because we're reaching the point where we can have 99% agreement with a public or expert classifications. And you think that what kind of improvement are you getting at that stage? It's that idea of, it doesn't have to be perfect. Don't strive for perfection, strive for done. But at that stage, as we're talking about these surveys that are of 1 billion galaxies, and 99% means you'll still have 1 million left. It's almost like, how can you reach that improvement level where you reach a number that isn't quite as scary as still having 1 million left to classify? We know it's doable, but if it's scalable in that sense is difficult to know. I definitely like to see improvements on picking out much fainter features in images. So one of the things people look for is, yes, okay, you've got the glaringly bright galaxy, but perhaps you might have something like the Magellanic Clouds around this galaxy. So for those in the Southern Hemisphere will know what I'm talking about. These are 2 little dwarf galaxies that orbit the Milky Way, and they're slowly sort of being torn apart by the Milky Way's gravity. But they're so much fainter. Like someone, observing who's in Andromeda right now, say they're in a planet in the Andromeda galaxy, looking back at the Milky Way, would probably find it very difficult to see those trails, right? And so you have to observe for a very long time to be able to see them. Getting an AI to look for them is difficult when they're that faint. You obviously have to feed and train the AI on very obvious examples, very faint examples as well, and getting to pick that out. I'd love to be able to see an AI that could pick out something like that, or even pick out the weird things, like, here's something that doesn't look like what you told me to classify. I think it's the unknown knowns that are buried in the data that it would be great if an AI could pick out, but I just don't know how it would do it.
I want to go back again, I guess, to what's familiar for me, which is what I remember as a child. I would look up at the sky and I would think, I'm looking directly at anything I'm seeing. There's nothing between me and what I'm looking at. But from your description, we are sometimes looking at one galaxy through other galaxies. How do you train AI to deal with that?
Yeah, that's another thing. It's almost like distraction, isn't it? So there's a really famous object called Hoag's object, and it's a very strange galaxy. It's what's called a ring galaxy. It has sort of this core to it, and then it's surrounded by this big, bright blue ring. And it's perfect. The ring is unbroken. We see it completely face on as well. And it's an incredibly rare type of object. And inside that ring, in what you would think of like as the empty space between that sort of core and the ring, there is another ring galaxy in the very distance. It's phenomenal. And you wonder whether, okay, well, if you trained a machine on that image, would a machine only classify a ring galaxy if it had another one, in the empty space of the ring? Or would it always miss those little ones in that empty space and stuff like that? So that sort of like distraction of an AI, or, you know, maybe perhaps you're looking for something specific in a galaxy, but it was been missed because it's merging with another one. I think distraction is a huge thing in AI. The fact that you could be looking for one thing, but because it's near another in the sky, it gets ignored.
And I have a question also that just comes from my fascination with cameras. Different cameras and different lenses render light differently.
Mm.
In creating these data sets, do you have to deal with biases that may enter because different telescopes gather the light, different cameras were capturing the image? How do you, to what extent does that cause a problem, and how do you deal with it?
I mean, that's basically like the history of astronomy and the history of CCDs. We could be here forever, right? One of the main things is aberrations through the lenses. So you don't get a perfect image. You might get what's called an airy disk, where you get sort of rings surrounding your main image. That's a huge problem, but that's been solved for a long time. It's something that Fourier transforms, the magic of Fourier transforms, anybody who knows what that is will know they are magic, can remove. And so there's lots of things like that. There's also obviously atmospheric turbulence to deal with when you've got a ground-based telescope. You can think of even, you know, when the Hubble Space Telescope was first launched, the mirror was deformed. And so it wasn't giving us, a clear enough picture because the light was bouncing off something that was deformed. There were ways to correct that, but it still wasn't great. But one thing that amazes me now is something called adaptive optics, which are on a lot of telescopes. Have you ever seen an image of a telescope that's firing a laser into the sky? And you're like, well, why is that telescope firing a laser into the sky? It's basically creating a fake star. And we know that laser should be a perfect point of light that the telescope will observe, right? But instead it will be distorted in some way. And that's because of the atmosphere that it's traveling through. Your turbulence on a plane, right, is caused by different pockets of air that are of different temperatures and pressures, and that the light gets, disturbed in the same way as it passes through that air towards us. And so if you can record the disturbance that the laser is experiencing going through that atmosphere, and you can correct your mirrors to account for that distortion. You can literally deform your mirrors to be like, oh, well, that light's going to bounce, and then that'll give us that clear picture of the laser again. You know that the light coming to a telescope from something else, from a star, from a galaxy, is going to have the same distortion on it and then be corrected in the exact same way. And usually that had to be done after the observations, but they can now do it in real time. They have real-time deformable mirrors on the back of telescopes to account for that kind of stuff. And again, that's usually like an algorithm that's running in the background making those decisions. And that still doesn't fail to blow my mind every time I think about it.
It sounds like a partial answer to the question I'd like to ask next, which is, what are the most exciting new instruments coming to your field in the next several years? And how will they improve the data situation? For example, you mentioned in a May 2021 YouTube talk that the James Webb Telescope is set to, quote, revolutionize nearly every field of astrophysics. Could you tell us why, and what other instruments might be on the horizon?
Yeah, so James Webb is going to be a huge one. It is sort of been plugged as like the successor to Hubble, but it's nothing like the Hubble Space Telescope. First of all, it's much bigger than Hubble. Hubble is only a mirror of 2 meters across, so that's its collecting area. I love the t-shirt, Mark. Nice. Mark's got a James Webb t-shirt on. Hubble is only 2 meters across, whereas James Webb has a 6-meter telescope, 6.5 meters. What that means is that its collecting area for light is bigger. So it can collect more light, which means it can see fainter things. So that's great. You see fainter things with James Webb than you do with Hubble. Hubble looks in optical light. Mostly optical, a little bit of UV, and just brushes the infrared part of the spectrum as well. So the bits that sort of, bookend the optical visible part of the spectrum that we actually see with our eyes. James Webb is just infrared. And most people are like, why then? It's seeing stuff that we actually wouldn't be able to see with our own eyes, but actually it can tell us way more information with infrared. First of all, dust blocks infrared. And when I say dust, I mean like gas that has heavier elements in it, like iron and carbon, that might have clumped together to give you something bigger than just an atom, right? It's a little particle of maybe carbon clumps or something like that. The less glamorous term for it, supernova poop, because this stuff's made in stars and then thrown out by supernova. That's what I call it anyway. So dust blocks visible light. It doesn't block infrared light, though. The infrared light just goes right around the dust, the supernova poop. So that's great. It's going to let us see inside very dusty regions. Dusty regions are where stars form. So that's one thing that James Webb is going to be able to do. Also, because the universe is expanding, light gets redshifted. So as galaxies in the very early universe give off their light in visible wavelengths, by the time it reaches us, it's infrared. So there's literally a limit to how far you can see with Hubble, because at that point you won't receive any more light from that galaxy because you physically can't see it anymore because it's all in the infrared. So James Webb will be able to see way back further than Hubble ever has been able to. And we hope back to sort of the formation of the first stars in our universe. It also, in the infrared, can pick up water absorption features. So all elements and atoms and molecules absorb a specific wavelength of light. It's sort of like the light that they're akin most to, right? It gives them the energy they need at a very specific wavelength to vibrate in a certain way. And so if, for example, you were observing the light from a star that has passed through the atmosphere of an exoplanet orbiting around it, and just that little wavelength of light that we know water absorbs just disappears in the light that you detect with the James Webb Space Telescope, you know water is there on that exoplanet. So everything from planets to seeing the most distant things in the universe is what James Webb is going to do. And this is why people are so excited about it. It now has a launch date of the 18th of December. So that'll be a very nice Christmas present if all things go smoothly for astrophysicists. And James Webb, I think, is the one that gets talked about the most. But we have so many other facilities coming online. The Vera Rubin Observatory that we've talked about, but also the extremely large telescopes, both the European and the one that's being built in Mauna Kea that's had some legal troubles to it, rightly so. And also on top of that, you've got a load of radio telescopes coming online very soon. The Square Kilometre Array is coming online very soon across South Africa and Australia. They're going to revolutionize radio astronomy like has never been seen before. Like the most incredible amount of detail on things that give out radio emission, which are some of the most energetic things in the universe as well. Things like black holes and neutron stars and stuff like that give off radio waves. So that's going to massively transform things. And then the one thing that I'm very excited about, we have these gravitational wave detectors on the ground at the minute. They're basically big L shapes of mirrors that detect when the distance between those mirrors gets squashed or shrunk by gravitational waves. But they're only sensitive to certain frequencies of gravitational waves, the frequencies that are given off by stellar mass black holes merging. But supermassive black holes merge too, but give off different frequencies. But to detect those, you need a bigger detector, bigger than you could probably build on Earth. So we are planning to build one of these huge, big L-shaped detectors in space. It's going to be called the LISA Observatory. I can't remember what LISA stands for off the top of my head at the minute, but it's a collaboration. I think it's the ESA's observatory that they're planning to build, the European Space Agency. And I'm so excited for it. The idea that we could detect gravitational waves from supermassive black holes, my baby's what I study first, but also that we'd have this huge contraption in space that we'd managed to build. And that's quite far in the future. I don't think that's going to be until the late 2030s that's really realized. But the fact that is sort of being decided on now and sort of being pushed forward is really exciting.
Because Webb has had so many delays, I have to ask just a couple of other questions about it. How is it going to filter out the infrared noise creation from the Earth and from, of course, our sun?
Mm-hmm. Yeah. So first of all, from Earth, it's actually going to be many millions of kilometers away from Earth. So that helps. It's at something called L2, which means it's essentially going to trail Earth in its orbit around the sun. So it'll be protected from Earth's infrared source. Of course, the sun is not something you can really escape in the solar system. So it also is equipped with a essentially giant sun shield, is what you can call it. It's about the size of 3 tennis courts. It's huge. It has to be folded up inside the rocket. And when it gets to the location in space that it's going to orbit the sun at, it will unfurl very, very slowly. And this is one of the reasons that people are quite nervous, because things could go wrong with that unfurling. And it needs that sun shield to operate, because all of the instruments that detect this infrared light are cooled down to, a couple of Kelvin essentially to be able to function. And so shielding, and that shielding actually working is very, very important for this telescope. And I think it's many layers thick as well, this sun shield, and it should be able to filter out all of the infrared from the sun so that does not interfere with its observations.
And is space sufficiently large that we don't have to worry about things hitting it and puncturing it?
Yeah, exactly. I mean, it's very small. First of all, it's not like Earth, where Earth might have a stronger gravitational field to pull things in that might be nearby, little asteroids, things like that. But also they do have some control over it. So if we think that there's something on a trajectory with it, we could always give it a little nudge and a little push either way with some little thrusters as well. So I don't think that's anything we have to worry about, she says. Fingers crossed.
Well, I'd like to circle back to the beginning of our talk, because we mentioned this question in our introduction. It's now thought that there is a supermassive black hole at the center of every galaxy in the gravitational driving sea of the whole star system. So which came first, the galaxy or the black hole?
I wish we knew. And this actually might be something that James Webb, the Space Telescope, can tell us, actually. So, I mean, this question comes from sort of thinking about the very early universe, the first stars forming, the first galaxies of stars, these collections of stars. What pulled together that collection of stars? Did the gravity of the stars themselves keep them bound? And then did one star go supernova and become a black hole and sink to the center of that system and became the thing that everything orbited around? Or did, say, a gas cloud in the very early universe collapse straight down into a black hole, and then that shepherded a load of hydrogen gas around it that's the first stars formed from and created a galaxy that's always been orbiting around this black hole? It's the astrophysics chicken or the egg, right? We're not entirely sure which one came first. And the only way we know of that you can make a black hole is if something goes supernova and forms this black hole. Not something, a star goes supernova and forms a black hole. So this idea of a gas cloud collapsing straight down is theoretically possible, but we've never observed anything like that happening before. The only way that would happen is if the gas cloud was prevented from making stars first. And to make stars, rather unintuitively, you need cold gas rather than hot gas. Everyone's like, but stars are hot. Surely you'd need hot gas to make stars. It helps them along. But actually, you need very cold gas. You need the molecules in the gas to be traveling quite slowly so that gravity can actually pull them together. If they're traveling very fast, then gravity's got no chance. It's just going to fly off and ping off and it's not bothered. So very cold gas will bring that together and make it collapse and form a very dense region where you can trigger nuclear fusion and you form a star. If you have two clouds of gas next to each other, one of them collapses down and makes stars first, that will be like radiating that other cloud of gas and making it energetic so it stops collapsing under gravity. But then you've still got this rather large clump of gas that still has its own gravity, and it'll start collecting more and more and more gas until eventually it reaches some critical mass and could collapse down into a black hole, is the idea. If that gas is being radiated, it should glow. It should glow at very specific wavelengths because it will just be the hydrogen that's glowing at a very specific wavelength. It shouldn't be any stars giving off, light across the whole spectrum of sort of optical light. And so we should be able to pick that out with something like James Webb. So that would be one way that we could prove, okay, if we can find these things. And there was sort of maybe a hint that Hubble kind of found one, but again, it's the infrared, you need to confirm it. If James Webb could find these things, that could answer that question of what came first, the galaxy, the black hole. And if it found them, we could be like, the black hole comes first, because here's this gas cloud that's about to collapse and about to become the center of a galaxy, and then stars are going to form around it.
As a person who brings to her subject more enthusiasm and excitement than I think I've ever seen from an astronomer, which are you more excited about? The prospects of what these the telescope instruments are going to bring to your research, or the improvements in AI?
The telescopes. I'm so sorry, Charles. I'm sorry, but it's the the AI is great, but the AI is a tool at the end of the day, right? Yeah, it's like, someone saying, what are you more excited about, seeing these things or the statistics? Seeing these things, right? I'm not going to get excited about the statistics, which to me is a similar tool. I think it's very exciting to think about what advancements in AI will get and where that will feed into society. And I think that's always the sort of justification that I give for why do we bother doing astronomy? Why do we fund all of these new instruments? And why do we bother asking these big questions about space? You don't know where they might lead. Astronomy led to the development of a digital detector, which now everyone carries every time they take a picture, right? In your mobile phone, you have a camera, and that came from astronomy. Radio astronomy needed a way to combine the signals that they were getting from all their radio telescopes so that they wouldn't be really weak. And that ended up giving us Wi-Fi, because before that, all of the signals from Wi-Fi would bounce around your house and be really weak by the time they got to your computer or laptop. Your computer or laptop uses the same thing in radio telescopes to combine those signals to get a strong one again. And then all of these image processing techniques, are fed into medical imaging, sharpening images, getting rid of noise, in an MRI or a CT scan or something like that. Data storage and data processing, is going to be a huge one going forward as well. And we're the ones taking the biggest data sets, so we're going to be pushing that forward. So I'm really excited to see if we do end up pushing one little bit of, machine learning techniques forward, what that will then enable us to do, especially with imaging, whether it's maybe, before and after pictures of, say, where satellite imaging, where a hurricane or an earthquake has struck or something like that, developing machine learning so that can, actually figure out if there's somewhere on the ground where first responders need to get to, something like that. Like I'm really excited to see that kind of side of things, but I'm just so excited for the science results that are going to come off the back of all of the new observatories and facilities that are coming up in the next decade, 2 decades. And the ones I don't even know to get excited about yet, because they're still just an idea on a piece of paper.
Well, I hope as they do, you'll give us an opportunity to read another book by you, because your first book, and when I said can be read in an evening, I probably wasn't fair, because I took several because I just enjoyed mulling over each chapter after I read it. But you've been a fascinating guest, and we're honored to have you accept the invitation. It's been a delight to talk with you. Thank you so much for taking the time.
It's been great. Thanks, guys.
Yes, thank you, Dr. Smethurst.
The views expressed in these podcasts are solely those of the speakers and not of their employers or organizations. We thank the American Bar Association for their generous sponsorship and support of the production of this podcast. Our theme music was composed and performed by the very talented Ben Rosenblum. We welcome questions and comments from listeners. Send email to comments@mindthegapdialogues.com. We read all comments and questions, and will try to respond in the letters section of a future episode. If you are writing about a particular episode, please do mention the specific episode number. Please also do include pronunciation tips to help us properly say your name when we reply in a subsequent episode. See you next time on Mind the Gap Dialogues on AI.
Thank you for listening to the ABA Business Law Section's podcast series, To the Extent That. The section offers a robust collection of content. To explore more about this topic, or to learn about joining the section, visit ambar.org/bizlaw. That's BIZLAW.